each individual or some sample of the individual populations, samples of the red population, firing, not firing, firing, not firing, and so on. And the distribution in this case looked quite log normal. And he did examples of doing Levelt's proposition 2, where he changed the stimulus, okay, to population B, keeping the stimulus to population A fixed. And here you see it hardly changed the mean duration of the B population, but increased the period of the dominance duration of the A population. It automatically satisfied Levelt's proposition 2. Okay. There are MRI experiments taken when humans are doing these tasks, as well as monkeys doing this task, to see regions that are alternating with each other. And in fact, there's some electrophysiology data. Logothetis has been able to somehow train his monkey to report his perception. Okay? And in that case, you will see alternating electrical activity as well, even as far down as in thalamus, I believe. Okay, so now we wanted to compare our modeling results with these two different frameworks to the experimental data that we observed. So we are choosing here something like Levelt's proposition 4, okay, equal input strength to the two populations, and we're going to change the adaptation strength as a parameter, because we're going to move the model from winner-take-all regime to an oscillator regime. And then we'll add noise. Okay? So if the adaptation strength is large, the system will oscillate. Okay? The adaptation can always overcome the stimulus or the inhibition. But if the adaptation strength is weak, then you get stuck in the attractor-dominated regime. Okay, so here you see these different regimes of oscillation. If I increase the strength, oscillation, winner-take-all, oscillation, and symmetric steady state, both high. Okay, so now we're going to add noise to this system. And these are sort of the ranges of statistics that we see for, I think it's probably from the Plaid experiments. Mean dominance duration on the order of some seconds. Coefficient of variation, that is standard deviation over the mean on the order of about 0.4 to 0.6, 0.7, something like that. So these are two statistical constraints. So now we add a certain amount of noise to the system over this two-parameter plane, and we ask, where do we satisfy this mean period within those two constraints? And it is this regime right here, looks like a horseshoe. Okay. If we ask, where is our CV constraint satisfied? Okay, between 0.4, well, we actually put 0.8 down for the model. It's also a U-shaped region. So if we overlay those two regions, we will satisfy both constraints. And it would tell you the operating range of where the model would be consistent with the statistical data. Okay, so I've repeated those. We overlay them, and that is this green region right here. It's a small parameter range for the adaptation strength in order to satisfy both constraints as we increase the input strength to both populations. If we increase the noise level, okay, that green region of interest expands. It's easier to satisfy those statistical constraints if we increase the noise level. Increase the noise level more. Okay, so what we're seeing from this is that the region of interest lies primarily in the attractor-dominated domain, okay, but also near the boundary between oscillator or attractor-dominated regime. So our conclusion, at least for this simple model, is that attractor-dominated behavior seems not unreasonable to put your bet on. Okay. I didn't say, let's say one more thing. Think about this. If there's a slow negative feedback, like this adaptation variable, you would expect the following thing to happen. If I have a short dominance duration, okay, it means that one population didn't have much time to adapt, and the other population didn't have much time to recover. So when there's a switch, the other population is going to still be fairly adapted. And it should also have a short duration. So there should be some correlation between dominance duration in this cycle and dominance duration in the next cycle. In looking at many different data sets, people report no correlations between one dominance duration and the next. Suggestive that, well, maybe there's some mechanism to do almost an instantaneous reset, or that the noise is so dominant that that picture of the adaptation is not reasonable. Okay? All right. So we're going to talk about Lavel's proposition 2 now. Okay? Again, recalling, and this is from our experiments with binocular rivalry. If we hold the contrast of A fixed and decrease the contrast of B, we hardly change its mean dominance duration, and we increase the dominance duration of A. Okay? Decreasing the contrast to B decreases its fraction of time dominant. That's the intuitive thing about weakening B. Okay? So this is the way Lavelle did the experiments and the way other people did. Well, what happens if I increase the contrast of B? Okay? Do I say that if I increase the contrast of B, B hardly changes, but the dominance duration of A decreases? Okay? B would still be stronger in that sense because it would have a larger fraction of time dominant, but what is happening? Okay, well, it isn't this. Okay, so let me show you how we change different parameters to bias the system one way or the other. Okay, so here we have two different wavelengths. Okay, so now we are having we're biasing the system toward transparency, but we're also biasing the depth Q by making the wavelength of one shorter than the wavelength of the other. So for most of us, it would appear that the short wavelength grading is behind. Okay, it's sort of an aperture kind of effect. Oops, move it. Ah, is this the same one? Okay. Okay. Do you see any switches in this one? Any switching? Okay, so this is pretty strong. Okay, how about this one? This one you can see some switches in. Okay? But it's still a little bit biased toward the short wavelength. So this is an example of doing an experiment like Lavel's proposition 2. Okay, so here we've now plotted these data for the depth reversal case. Okay, decreasing the wavelength of one does exactly what Lavelt's proposition would say, but now changing that same way.